Remember that while discussing binary search trees, we said there are two different ways of improving the performance. One was the radix search trees, or radix searching in general, and the other approach was balancing the tree, keeping the tree balanced all the time. And the solution there, we said, was the AVL tree. So this is where we discuss AVL trees. So first look at the size of a binary tree. A binary tree is composed of actually a root node and its left subtree and the right subtree. So if you can find the size of the left subtree and the size of the right subtree, then the size of the whole tree would be the sizes of the sum of the sizes of the left and right subtrees plus 1 for the root node. And you can find the sizes of the left and right subtrees in a recursive manner this way. Because finally, if you make it smaller and smaller, at some point it will be left with only one leaf node, which will be 1, and from there you can come back and find these values. How about the heights? Actually, the height is also similar. A tree with a root actually has a left subtree with the height of HL, let's say, height of left subtree, and another subtree for the right subtree with height h of r. Now the size of the whole tree, which is actually merging the left and right subtrees under the root, would be one level higher than this. Higher than what? Whichever one is greater, that value plus 1. Therefore, it would be the maximum of HL plus 1 and HR plus 1, whichever it is larger. Or you can also look at it this way. It would be maximum of HL and HR, one of these, plus 1. Same thing. So let's now define a balanced tree. We say a tree is balanced if the height of the left subtree and the height of the right subtree are not exactly equal, but very close. And we will say with a difference of at most 1. So if the left and right subtrees of the root are equal, or the left subtree is higher by 1 level, or right subtree is higher by 1 level, we will consider them to be, we will consider the whole tree to be balanced. Note that we're not enforcing exact equivalence, and there's a reason for this. Because there might be cases where one of these subtrees, say the left subtree, is higher by 1 level. When you try to balance it, it might happen that now the right subtree is 1 level higher. Then you will again try to balance in the reverse direction, and then again in this direction. So there will be what we call a hysteresis effect. You will never be able to finalize this. It will be between these two. So you will keep on balancing, and balancing will never end. Therefore, we say if the difference is only 1 level, that's sufficient for us. We will consider them to be balanced. In general, if you look at the trees visually, the balanced trees look a little bit wider and flatter, whereas the unbalanced trees typically look accumulated to one side. But note that the visual look sometimes might be causing some misinterpretation, as we will see with the examples later. So consider the trees composed of 3 values in here, in parts A, B, C, D, E. Okay, so we just have the values 1, 2, 3 in all of these trees. Okay, Now, let's look at the first one, part A. How would this tree be formed? I can conclude that the input was in the order 1 first. So initially, it was a completely empty tree. Okay. So when it was completely empty and input 1 arrived, it would be placed. When 2 comes, 2 has to go to the right of this because 2 is larger than 1. And 3 comes, when 3 comes, that will have to go to the right of 2. So that's what we have in part 2. So what can you say about the order of the input in part B? Obviously, it was entered in the order 1, 3, 2. Because if it was entered in the order 1, 2, 3, 2 would be at the second level, and 3 would be the child of 2, because it would come later. Okay, so I know that it entered, the input was entered in the order 1, 3, 3, 1, 3, 2. If the input was entered in the order 3, 2, 1, for example, I would have part E, right? How about part D? It was entered in the order 3, 1, 2. How about part C? Now, part C is slightly different. Can I say it started with 1? No. If it had started with 1, 1 would be at the root. If it had started with 3, 3 would be at the root. So since 2 is at the root, I know it started with 2. Then, so it would be like 2 is placed here. If the next input is 1, so it's in the order 2, 1, 3, 1 would be placed here and 3 would be placed here. However, if the input was in the order 2, 3, 1, what would be the difference? 2 would be again at the root. When 3 comes, 3 would be to the right of 2, and 1 would be coming to the left of 2. So it's the same thing. Therefore, so for this one, it was in the order 1, 2, 3. So thus, I can conclude that, let me just erase these unnecessary ones. Now I can conclude that the input of order 1, 2, 3 caused A, 1, 3, 2 caused B, whatever. Now for C, I have 2 different possibilities. I have 6 different combinations. So the probability of observing the first 3 would be 1 over 6, 1 over 6, 1 over 6, 1 over 6. For this one, it would be 2 over 6, which is equal to 1 over 3. So in other words, the probability of observing the 3 in part C is twice that of seeing any other of these 3s. Sorry. So what we observe is that the binary search trees are balanced, that are balanced will have log n search time. Why? Because since they're balanced, in every comparison, you will be getting rid of almost half of the search space. So with log base 2 of n comparisons, you should be able to find what you're searching for. So therefore, it is desirable for us to have the binary search trees as balanced as possible. We have been discussing this all the way. Well, how do you do that? Well, you will be actually harming the balance when you do an addition operation or a removal operation. When you insert or remove an element to or from the tree. So you will have to modify your insertion and removal operations such that the tree, even after an insert or remove operation, remains balanced. And in 1960, 2 Russian mathematicians were able to devise the algorithm that would achieve this. It's one of the several known auto-balancing tree algorithms. There are other alternatives, but this is the most famous one. Auto-balancing tree means a tree that balances itself after every add or remove operation. So we will first define the concept of balance factor to discuss how we do balancing. So the balance factor is you take the height of the left and right subtrees for node n. So for each node, we are defining the balance factor. And for that node, you take the height of the right subtree and the left subtree, subtract the height of left subtree from the right subtree, and you will find the balance factor of that specific node. And remember, by definition, the height of an empty tree is -1. So a binary search tree is an AVL tree if for all nodes in the tree, the balance factor is either 0, which means the left and right subtrees are of the same height, or 1 or -1, which means the difference between the heights of the left and right subtrees cannot be more than 1. And this is how actually, remember, we defined balanced trees. So let's see some examples. The tree in part A, although it may not look balanced to you, that's why I said that visual input might be somewhat misleading. This tree seems to be heavier to the left, right? Because we appear to have more nodes to the left. However, if you look at the balance factors will show that it's always, there are no nodes here that have balance factors greater than 1 or less than -1. They're all 1, 0, and -1. Like if you look at 16, it is, remember, right minus left. So it is 0 minus 1, 16 is -1. How about 12? To the right, the height is 2. To the left, the height is 1, 2, 3. So it's 2 minus 3. It's -1. So it's still acceptable. Note that if 14 was removed, then it would be unbalanced. So this tree is currently balanced, but it's very close to getting unbalanced if 14 gets removed. But it hasn't happened, so still it's a balanced tree. If you look at this tree now rather than removing 14, if we add, now remember this side is more heavier, right? This path is longer. If you add something here below 2 or 6, the left subtree of 12 would have a height of 4, whereas the right subtree had 2. Therefore, the tree would be unbalanced. But note that if a node is added below 10, it would not unbalance it. So we cannot say all insertions cause the tree to be unbalanced. So you don't do the balancing if the insertion did not cause an imbalance in the tree. You do it only if, because of insertion, the tree now becomes an unbalanced tree. Okay, and note also that when you insert 1 here, it's strange that you insert a single element, but 2 nodes, both 8 and 12, suddenly become unbalanced. Why? Because for the case of 8, here it was 1 minus 2, and you added a new element to that larger side. So it became 1 minus 1 minus 3 now. Therefore, 8 also becomes unbalanced as well as 12. So we should find a solution for both of them. So here are some more AVL tree examples. Here, the values in the, inside these red circles are not the values to be stored. They're just showing the balance factor. So it's not important what's written in here, what the value in the node is. The important thing is the balance factor. So it's just given here are the balance factors. As you can see, these are all AVL trees because you don't have 2 or minus 2 anywhere here. Whereas in this case, we have some imbalances. See, this is a very small tree, but this is actually not a balanced tree because here we have minus 2. Here we have 2 and minus 2. This is also strange because after 2, you might be expecting to going to minus 2 in a gradual manner. Like from 2, you go to 1, from 1 to 0, from 0 to minus 1, then to minus 2. Not necessarily so. This has the imbalance towards its right. This has towards its left. Here also, note that having 2 here does not necessarily imply that its parent is also unbalanced. You have an unbalanced child, but the parent itself is still balanced because of these 2 nodes here. So that's also possible. So when you find an unbalanced tree, don't think that everything above until the root are also unbalanced. That's not true. These are just examples for you. Just try to fill in the values yourself to see what the balance factors would be. So if we look at the problem in a more generic perspective, there are actually 4 different cases for an imbalanced tree. An imbalance might have occurred due to one of these 4 cases. In this slide, we have 2. In the next slide, we will have 2 more. So let's look at these. Let's first look at 1. Then we'll go with the others. So it could be imbalanced because you insert into the left subtree of the node's left child. So you insert to the left of the left. So K2 is the root here. K1 is its left child. A is not necessarily a single node, but it's a subtree. That's why we draw it like a triangle here. Because something has been added to the very end of A, the height of A has decreased by 1. Okay. And earlier A was here. So with the increase, A went 1 level down. So the difference between this new level and the level of C, which is the right subtree of K2, suddenly became 2. Okay. Now, we should be able to solve this. And how we solve is as follows. Now, take it like this. Assume that these are rigid bodies. These circles are rigid bodies, and also the triangles. And these links are just like ropes. Okay. And earlier, you were holding from K2. That's why K2 was at the top. That was the root. So from K2, we had K1 hanging, and from K1, we had the subtrees A and B hanging. On the other side of K2, we had C hanging in the air. Now, this time, hold from K1 and shake it. Now, when you hold from K1, K1 will go 1 level up, as you can see in the right here. K1 goes 1 level up, and therefore K2, you're not holding from K2 anymore, so K2 will go 1 level down. Okay, but when K2 goes down, it also takes C 1 level down. It was here, it goes 1 level down here. By the way, when K1 goes up, it will be pulling A 1 level up. Thus, I will have the balance between A and C. Now, I have a minor problem here now, and that's the following. Now, when I hold from K1 and shake, K1 would be at the top, fine. K2 would be here, and C goes 1 level down. But when you hold from K1 and pull it up, okay, A comes here. C was also, remember, a triangle. A comes here, but the problem is, remember K1 also had B here, that B would also be here. But then K1 has 1, 2, 3 children. Then it's not a binary tree. We have a problem here. So once again, let me repeat. The problem arises from the fact that, let me just a little bit undo here. Okay. So remember, K1 had 2 children. When K1 goes down, goes up, it will have these 2 children, but K2 has now gone below K1, so it will have 1, 2, and 3 children, A, B, and now K2 will go down, K2 will come here. So K2 will be also its child. Therefore, it will have 3 children, which is not legal. And what we do to solve that is we just make K2 adopt the previous child of K1. So when K2 goes down here, remember K1 should have been attached here. We just break this link and create this link. So K2, the tree in the middle, becomes adopted by K2. Okay? And this solves our problem. Now it's a balanced tree. Now, I hope you all understand this. I will skip from case 1 to case 4 first, because case 4 is actually just the symmetric of K1. But before going into that, I forgot to mention one thing. What we did in here was we hold K1 up and K2 goes down. So what we did in here is we just rotated the tree this way. This is called a tree rotation, and this time I'm rotating to the right. So we call this a right rotation. We'll refer to that right rotation several times in the following slides. Okay. So now let's look at case 4, which is just the symmetric of this. Let me just see. Okay, case 4, sorry, is not drawn here, but case 4 would be just the symmetric you're inserting to the right of the right child. Okay. Let me. Yep. However, for the cases of 2 and 3, the problem is more difficult. One rotation will not be sufficient to solve it, so we'll have to solve it with 2 rotations, as we will see in the following examples. So, as we said, we're doing these with rotations to the left or to the right. The tree will always remain balanced after these rotations, and it will be able to do the operations in log n times, the search operations. So actually, the right rotation is explained in the slide once again. Drawing it once again, we're doing a right rotation. So K2 goes down together with C, K1 goes up together with A, B remains here, but B gets adopted. So this link here will be broken, and B will get adopted to the new node that comes here, which is K2. So K2 adopts, as you can see in the figure, K2 adopts K1, C goes 1 level down, A goes 1 level up, but still remains with its parent process, the parent node. The only one that gets adopted is the one in the middle. So, sorry. Let's see that with an example. We're given this tree on the left. So we start with this one. Actually, in the beginning, we did not have this. So assume this value 3 is not here. If 3 is not there, this is a balanced tree. Okay. However, when 3 is added, this value 3 is added, the tree becomes unbalanced because if you look at 13, it is 1 minus 1, 2, 3. So this is balance factor of minus 2. How about 7? It is 1 minus 2, it's minus 1, so it's not unbalanced. So what we need to do is a right rotation. And remember how we do that right rotation. Let me erase these. What we do is the following. Remember, we're going to hold from this one and shake. So 13 and 15 will go one level down. So 15 comes here and 13 will come here. 7 goes one level up. But when 7 goes, it will pull 5 here. And 3 here. So it's not here anymore. The only thing that we need to do now is remove this and attach it here. Now this looks complex. Here's the simple implementation of that. What we do is as follows. We're going to shift these two down. Okay, so we break this link between 13 and 7. We break that and shift this group 13 and 15 one level down, as you can see here. Take this group and shift it here. 7, 5. But to be able to do that, first you have to detach this. So the first thing that you do is when you decide to rotate 7 around 13, that's how we call it. 7 is the one that we're holding from and shaking. 13 is the old one. So we say the new parent is rotated around the old parent. So when we're rotating 7 around 13, first for the new parent, detach this node, this actually subtree, there could be several nodes here. I don't care, but detach this right child of the new parent and then do the shaking. And this detached node becomes the left child of the previous parent, which becomes the right child of the new parent. And that's what we see here. 13 and 15 are removed from 7 and taken one level down. This is detached and this group is shifted up. Then we create this link and take 10 here and attach it here. It's not here anymore. And that's the result, as you can see here. It's actually simple. So here we have another example. This is the initial tree on the left. We insert a new node here. If you look at the tree in the middle, after you do the insertion, suddenly the balance factor of 7 changes from -1 to -2. Therefore, it's not balanced. So I have to do a right rotation like this. So 7 and 9 go down. 1, 3, and 5 go up. And 6 remains in its place, but it gets adopted by the old parent. So easy. So this was for the right rotation. Another example. Now, if you look at the tree, the imbalance, the first unbalanced node is 8. Is 12 balanced or not? If you look at 12, it is 2 minus 1, 2, 3, 4. This is also minus 2, by the way. But I don't care. The first unbalanced node is 8. So first I focus on 8. I will solve this problem. Then I will try to solve the problem with 12. Okay? So focusing here, I need to look at this subtree, 12, 16, and 14. Just put them aside for the moment. We don't need to deal with that. We're just focusing in the tree in this rectangle. So this tree is unbalanced, and what I need to do is rotate 4 around 8. So 8 and 10 go down, 1, 2, and 4 go up, 6 gets adopted. Look at here. Exactly what I said. 8 and 10 go down, 1, 2, and 4 go up, and 6 get adopted. 6 was the right child of 4. Now it's the left child of 8. Okay? Now, and this new root, formerly the root was 8. Now here in this subtree, the root has now become 4. That one gets connected to the parent. Now that I have balanced this subtree, let me check the balance factors once again. Remember, this was minus 2, this was minus 2. If you check it, you see that this is now minus 1. Did I do any rotations on 12? No, no need. Because when I solved the problem here in this rectangle, this minus 2 was caused by this thing. And when I solved the problem in this subtree, that minus 2 became minus 1 automatically. So I don't need to do that rotation. So you should always check after each rotation if things are still problematic or they are already solved. So solving part of the problem somehow solved the whole problem for us. That's possible. So this is the code of doing the right rotation. As you can see, actually, it's just 4 steps. You can just go over the code. I will not go over the code, but as you can see, we just do 4 assignments, link updates, and that's sufficient for us. That's it. Because the algorithm itself was actually not that difficult. Now let's look at 4. As I said, case 4 is just the inverse of this one. This time we need to do the left rotation because see, part B is the before rotation, part A is the after rotation. So you first have part B. From part B you try to come to part A. So the insertion here, the insertion here at the bottom of C caused the imbalance at K1. So I need to this time rotate to the left. This is a left rotation. Okay. And what I do is, again, hold from K2 and shake. So K2 will go up, K1 will go down together with A, K2 will go up together with C, and this B, which is again in the middle node, this time gets adopted by the new node that comes here, which is K1. And this is what we have here. K1 adopts B, it has come down one level, and K2 goes up together with C, and we have a balanced tree. Just the same thing in the reverse direction. So the examples about that will also be simple. So very fast, again, we need to do, as you can see, the imbalance is at 50. So we need to do a left rotation. So 7, 80, and 90 go up, 50 and 40 go down, and 60 gets adopted. And that's what we have here. 70, 80, 90 have gone up. 50 and 40 have gone one level down, and 60 has been adopted, as you can see. And this is the code for the left rotation. It's again similar, just the links are changing, that's all. Now case 2 and case 3, now these are different. Single rotation would not be sufficient. Okay, like if you look at the figure on the left, we need to do a right rotation. Okay, so when we do the right rotation, K1 goes up together with P, it will go up. K2 and R will go down. K2 and R have gone down. K1 and P have gone up, but the imbalance was due to the Q here and remained in its place. Earlier, the imbalance was between Q and R. Now it's between Q and P. But the important thing is it is unbalanced. So it doesn't solve our problem. Okay? So that is not the answer to case 2, and similar is true for K3. They cannot be solved with single rotations. So how do we solve these specific cases? We need to do 2 rotations, and these rotations are either left-right or right-left. You never have left-left or right-right rotations. So these 2 rotations will be the other way around. So what we do in here is we rotate to the right. Sorry, if you look at here, we first focus on, oops, let me get the marker. We first focus here, okay? We do a right rotation in this one. So K2 will come here. This will be K2. Or let me show it clearly. K2 will go up together with C. K1 will go down together with A. And B will get adopted here. So what I will end up with, there would be K2, K1, A. B gets adopted by K1, and K2 has C here. And remember, it was connected to K3, which is connected to D here. Now, this is a problem I know. I can solve this problem with a right rotation. Because when I do that, K3 and D will go down. K2 will go up. Okay, so K3, pay attention, K3 goes down, as you can see here. K3 goes down, K2 goes up, together with, now I can look at this thing as a single group, together with the 3 rooted at K1, it will go up, and C will get adopted to the new node that comes here, which is K3, and that's what happened. K3 and D went down. C got adopted by the new node that came here, which was K3. And K2 went up together with its left child, which was the subtree that was rooted at K1. So with K1, it went up. When K1 went up, A and B also go up. Okay. So this is, as you can see, first here we had a left rotation, and then we had a right rotation. Okay, therefore it's called a left-right rotation for the case of case 2. For the case of case 3, it would just be the inverse. There we will need a right-left rotation. So here's the example. The imbalance is actually here at 13, but First, I do a left rotation here. So 7 and 10 go up, 5 and 3 go down. Now, see, there's something interesting here. The left child of 7 gets adopted by 5 that comes here. But the left child of 7 was null. It was empty. That empty tree gets adopted by 5. So that's why you don't see it. But this will do a, as you can see, this will do a left rotation. Once this is done, now we do a right rotation. So 13 and 15 go down, 7, 5 and 3 go up, and 10 gets adopted. Once again, don't forget that there was an invisible null pointer here, which became the child here. Okay, but you don't see that. Again, another example. See, the imbalance is caused by a node that's getting inserted into the middle tree, not under 2, but under 6. That's why we need that double rotation. So again, we try to solve the problem here, but first we're going to do solve it here. Once we solve it here, then the other part will be solved. We first do a left rotation here. So 6 goes up with its non-existing child. 6 goes up. 4 and 2 go down. And 5 gets adopted by 4. And then when you're done, you do a right rotation. Remember, 6 had taken place of 4 here. You do a right rotation here. So 8 and 10 go down. 6 goes up. And 4 is its new left child. It goes up. For the case of case 3, as I said, it's just the symmetric of that. But now you have to do a right-left rotation. So that means you first do a right rotation here. K3 and D go down. K2 and B go up, and C gets adopted by K3. And then you do a left rotation. K2 had come here, so K2 now moves to the top. K1 and A go down. And B gets adopted by the new node that comes here, which happens to be K1 that's coming down. So as I said, it's just the symmetric of the previous one. So here we have an example. Again, you first do a right rotation here. So 13 and 15 go down, 7 and 10 go up. Again, the once you do this, you do this time a left rotation. Remember, 10 and 7 had come up. By the way, again, there was a null child here, which was adopted by 13 here. Once you do this, now you do a right rotation. So 15, 13, 10 go up, 5 and 3 go down, and 7 gets adopted by the new node that comes here, which happens to be the value 5. So for the implementation, these actually, now we've all explained it through figures. We said we're holding from here, shaking, whatever. Of course, you cannot hold and shake when you're writing your code using if statements. So for that, if we analyze it, we see that the cases are differentiated by the factors, balance factors we're looking at. For example, look at the simple one. For the case of case 1, a node n that has balance factor of -2 and its left child has a balance factor of -1. If this happens, that means it's case 1. So once again, when you see a node, you always start from the bottom where the node was inserted and you try to go up. While going from the point of insertion towards the root, on the way, when you see a node that is not balanced, which means -2 or +2, since they were all 0, 1, -1, they could not go to 3. They're either -2 or +2. So if you see a -2, then you immediately look at the left child. If the left child is -1, you say, okay, that's case 1, and I know how to solve it. Earlier we wrote the code for the right rotation, apply right rotation there. Now, if you see, again, a node with case -2, but its left child is not -1, but it's +1, then you say, oh, okay, this is a case 2. So in the case of case 2, I should do a left rotation on the left child of n, the one that has balance factor of 1, then a right rotation on n, which had -2. So with a left-right rotation, you solve the problem. However, if you, instead of -2, if you see a +2, but its right child has -1, then it will be case 3. Again, double rotations. If the node has the balance factor of 2 and its right child has balance factor of 1, then a left rotation, a single rotation, will solve it. After you balance the tree, you continue up the tree. What if nth child has a balance factor of 0? Just think about it, how that would happen. Or what if another imbalance occurs higher up? Just think about these. We'll discuss those later in the course. So this is showing those cases. These are just what I said are implemented here. Just you're calling left rotation or right rotation methods, which were implemented in the earlier slides. For the case of removal, we'll not go into the details of removal, but the removal from an AVL tree may also cause an imbalance in the tree. So, for example, this tree was balanced, but when you remove tree, then it becomes unbalanced. So again, you will have to do similar rotations to solve it. This is showing the results after a right-left rotation. For the case of removal, you perform normal binary search tree remove operation. Just remove that node from there, actually. And you update the heights from the successor node location upwards towards the root. Whenever you see a +2 or -2, then you apply the rotations. The remove also has 4 cases, and after rebalancing, you continue to the upper layers, but you should always recalculate the balance factors. Don't forget, after rotation, the balance factors will have changed on that path only, from there towards the root, not the rest of the tree. But for those nodes, you have to recalculate the balances. Now, in the next slide, you will see an emulator. This emulator was developed by a high school student, Oktay Çomu from Robert College, who was working with me. He's now doing his master's abroad. This is not a simulator, but it's an emulator. What's the difference? In the case of an emulator, it works like the real thing. So you just give, as you will see, you just give your own values, and it's just running all the codes. It finds the imbalances and does the rotations and shows you the result. The directives here explain how it works, so rather than going over them, I will just show you the emulator. You can just read the directives yourself to learn how to use it. So you start with an empty tree. You want to insert uh, values one by one. So let's first insert the values. Note that when I'm doing the insertions, I will not do the rotations. So I will end up with an unbalanced tree and then do the balancing. Let's say I insert, say, 50. So it placed 50 and the balance factor is, by the way, 0. Now I insert, let's say, 30. It goes to the left. 80 should go to the right. 70 should go between 50 and 70. Insert 90. And let's just insert a new node here. Let's make it simple for the moment, like 100. As you can see, before I insert 100, 30 has a balance factor of 0. Let me just zoom in a little bit. 50 has 1, and the others also have 0. So let me insert 100 here. Okay. Now 50 has a balance factor of 2. Let me start the rotations now. It has found that there is the imbalance. Okay. So by hitting continue step by step, it will work. It detached 70. Now it breaks the link between A and B. Now it will move 80, 90, and 100 up, 50 and 30 down, exactly as I said. Then it will attach 50 and 80 to each other. Now it is time to attach 70. Where should we attach it? Remember, it should go to the right child of 50. Now, is that correct? By the way, you should be careful. Why not here? Because if it comes here, it would mean if you connect 70 here, 70 would be in the right subtree of 80, which is incorrect. Because 70 is smaller than 80, so it should be accessed through the left subtree of 80. Okay? And now it's attached here, and we're done, so it has returned back to 0. You can just reset it. Now, let's enter a different tree, 60, say 80, 70, 75, 90, and let's insert something smaller than 60, let's say 40 here. Okay? As you can see, again, 60 is imbalanced. So note that this time it will require double rotation. So if I can somehow put all the load on the outer edge here, then I know how to solve it. I can just do a left rotation to solve it. So the first thing I'm going to do is rotate here towards the right in this axis here, rotate 70 around 80 so that I put the load on the outer right column. Okay. So we first rotate 70 around 80. So 90 and 80 will go down. 70 will go up. But 75 first has to be detached. So 80 and 70 change their places. Connect them. Now 75 gets inherited by 80. Now, as you can see, the load is on the right side, so I know how to solve this. With the left rotation, I can do it. Okay, so now I rotate 70 around 60. So 60 and 40 will go down. And now they're connected